Okay, Assalamualaikum warahmatullahi wabarakatuh. Selamat petang. Minta maaf. Having difficulty with my laptop just now. Tiba-tiba dia decide untuk hang. So, kejap saya set up dah.
Waalaikumsalam, Doktor.
Kejap Give me some time. Kejap. Okay, boleh nampak slide tak?
Boleh.
Okay, alright. Okay, Assalamualaikum warahmatullahi wabarakatuh. Again, alhamdulillah, wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi washabihi ajma'in. Allahumma shalli ala Muhammad wa ala alihi washabihi wa barik wasallam. Allahumma inni as'aluka iman nafi'an wa rizqan tayyiban wa amalan mutaqabbalan. Right. So today we're going to continue with the DC to DC converter part 2, in which we're going to look into a boost converter. Right. So I have to check first. So okay, we have international student here. Okay, right. Okay. So boleh nampak slide sekali lagi? Boleh nampak slide Right. So part 2 of the DC-DC converter, we will look into a boost converter, which is the step-up converter. So basically, we're going to step up. And kalau boleh, kalau kamu nak bagi tahu apa-apa, tolong cakap tau, sebab saya tak nampak view ni. Okay?
Boleh.
Boleh apa? Record tak nak? Boleh apa?
Tak ada apa, sir. Nanti kalau ada apa-apa, boleh bagi tahu.
Okay, right. So kalau ada apa-apa, please interrupt me, okay? Sebab saya memang fokus, saya tengok sebab saya punya setup dekat bilik ni, my setup I don't have the second monitor, so I cannot see whether you have activity, whether you want to ask question or put some question in the message box. So please, if you have something, just interrupt and ask if you want to. Okay, just interrupt me. No. The input voltage lah. So the output voltage is higher than the input voltage. So in this case, we look at into the voltage, right? So we cannot achieve this type of boosting capability using a low frequency transformer, but we can still use a transformer, but it is a high switching frequency punya transformer. But in this case, we're not looking into any half of the transformer. We just want to use the simple inductor for boosting up the voltage. And there are some assumptions that we have to do in which the analysis in steady state for continuous conduction mode, which means that the inductor current is always continuous and the capacitor is very large so that the output voltage is held constant and all components are ideal. Okay. So which means that we again so if it is this is the V out, what will happen is the output voltage will increase until the steady state. So this part we're not going to look into. We're going to focus into this part. Right? So this is the steady state region. Okay. And also all the components are ideal, which means that you can say that P out equal to P in, or the efficiency equal to 100%. And the switching period is T, and the switch closed for the time dt and open for 1 minus T. Okay. So this is the configuration or the topology. If you're talking about the power electronic, we call it a topology for the boost converter. So you have the inductor, the switch, the diode, the capacitor, and the output load. In this case, it is a resistive load. But the difference between the boost converter and the buck converter is the positioning of the inductor, diode, and the switch. Previously, in the buck converter, we have the switch here in this place, and we have the inductor here and the diode here. So we rearrange the positioning of the inductor, diode, and the switch. Then we get a new type of converter that are capable to boost up the voltage. So the terminology see, still this is I in, I out, and the capacitor current. Again, this capacitor is large enough so that the voltage, the output voltage is constant. All right. So there are two modes, of course, when the switch is closed and when the switch is open. Switch is on, switch is off, right? So what happens when the switch is closed? When the switch is on, the diode here will become reverse bias. Why? Although previously the diode is in this is anode and this is cathode. Okay, this is anode and this is cathode. So you can see that the current can flow, but during switch on, what happen is um, the current will flow in the easiest path. So the easiest path for the current to have a complete loop is through the inductor, the switch, and go back to the source. Go back to the source. So this is the lowest path. So therefore, the current will not flow to the to the diode, and the diode will become reverse bias. And during this time, the inductor will start storing the energy. It will start store the energy. Okay. So the mathematical representation of what is happening during this time is we have VL, which is the voltage at the inductor, equal to Vs. So this voltage, this inductor voltage will equal to V inductor or VL, and equal to L di dt. And this is the typical, or this is the voltage for the inductor. Then from there we know that the IDT is theta I, the rate of current change in the inductor over the dt, which is the period of the switch, the time period for the switch to be on. And you have delta IL over dt and equal to Vs over L. So you bring L here to the left side, then you add delta I over dt equal to Vs over L. And from there we can see that the rate of change of the inductor current will become Vs over L times dt. So during this time, what will happen is the inductor current will increase. Okay. Now we go into the condition where the switch is open or the switch is off. So when the switch is open, the input voltage and the energy within the inductor need to be discharged, and it forces the diode here to be forward bias, and the diode is on, and there is no switch here because the switch is off. And now we will have V in and Vs series in each other. So VL in this case, Vs minus V naught equal to L di dt. Right. So delta IL over dt equal to delta IL divided 1 by 1 minus D, which is the time for the switch is off times the total time. And what we get, Vs minus V out over L. And from there, we manipulate the equation. We want to see what is this IL. And this IL will become Vs minus V naught V out times 1 minus D times T divided by L. So in this case, during this time, the current will start to reduce. Right. So the law for the inductor that it cannot store energy for a long time. What will happen is the sum of the energy inside the inductor for one complete period will be 0. So in this case, if we add uh, the current when the switch is closed and then when the switch is open, so what will happen is we have Vs over L, Vs dt over L, which is this term, plus this term, plus this term will equal to 0. So from there, we can see that Vs time dt, Vs minus Vs time minus dt, and this is Vs dt, so you can cancel each other. This one, what will what we left is this term Vs, V naught, and L and D. So if you manipulate this equation, then what you get is V naught equal to Vs over 1 minus D. So how can it has the boost capability? So let's say if you have V out equal to, let's say in this case, let's take D equal to 0.5, V out will be Vs over 0.5. So equal to 2 times Vs. So you can see that V out is twice the input voltage. For duty cycle equal to 0.5. In reality, what happened is you have a voltage here plus a voltage here. A voltage here. So you have this voltage plus this voltage equal to output voltage. And this voltage, the inductor voltage, will depend on how long you switch you let the switch to be on. So in this case, that's how we control the output voltage. Okay, boleh faham tak? So far so good?
Yes, sir.
Boleh. Sebab tu saya tak berapa suka online punya kelas, sebab saya tak nampak muka kamu, sama ada kamu blur ke tak. Tapi tak apalah. Hopefully minggu depan boleh kita face to face balik. Okay. So the input current now is the same as inductor current. So IS equal to IN because the inductor is in series with the source. So IS equal to IN equal to IL. The average power supplied by the source is the same as average power absorbed by the load resistor. Because we assume that this is an ideal case or ideal converter. So the average power supplied by the source is the same as the average power absorbed by the load resistor. So V out equal to V out over R, V out squared over R or V out I out, and P in equal to Vs I in. So in this case, we can see that the average current for the inductor become V out squared over Vs times R. Right. And again, when you have an inductor current, you will have a maximum current and the minimum current. And this is still bound to the operation mode, the CCM, BCM, and DCM. So for the peak inductor current, IL will be IL plus delta IL over 2, which is this is the DC component and this is the AC component or the ripple component. So in this case, what you have IL equal to Vs over 1 minus T squared times R plus Vs dt over 2L. Okay, actually this term is ds dt over L and divided by 2 because of this one. So then now it becomes Vs dt over 2L. And because of that, and this is to be IL mean equal to IL minus delta IL over 2 Vs divided by I minus T squared times R minus the Vs dt over L over 2L. So you can see that the current there. So this current is given by this equation and this current is given by this equation. Okay. What is the importance for this mathematical equation? Because you need to find what is the value of the inductor when you want to design the converter. Okay, for positive value of IL and IL max and IL min, the converter will operate in CCM. To solve the minimum critical inductor, the value that keep the converter in CCM, IL min is set to 0. Okay, the minimum critical inductor means that the inductor is the operation is BCM, boundary condition mode. So, or you can say that in waveform it is like this. So this is the boundary. When it is the boundary, the IL min equal to 0. So the minimum inductor value is given by IL min equal to R times the time divided by 2 times 1 minus T squared times D. Okay. To find if you want it to be in CCM, you have to increase the the minimum inductor value to 25%, which is, that's why you have this one. So this is for CCM to ensure CCM. So to ensure CCM, we increase L to 25%. Then your system will be in CCM. Right. So let's take a look at the waveform. The inductor current, we will have IL max and IL min. And for the inductor voltage, when it is connected to the source, we will have a positive voltage, and when the switch is off, then we will have a negative voltage. Right. So this is the diode current. Diode current only appears when the diode is on, so it is during 1 minus D times T. And again, for the capacitor current, we will have you will have something like this. So the question is why it is flat here? This region, why it is flat? Sedangkan capacitor dia tengah discharge during this time. Why it is flat? Kenapa dia maintain? Any idea? Any idea?
Hello.
Tak tahu sir.
Sir.
Okay. Jawab.
Hello.
Ya, dengar.
Dengar, sir. Could it be a constant discharge of current?
Yes, it is the constant discharge of current. Yeah. Because at the beginning we state the assumption that the capacitor is large enough so that the voltage is maintained, right? So because of that, the current is large enough to be flat here, to have a flat line. So maksudnya dia discharge energi yang banyak, yang mana current dia tak akan berubah terlalu banyak lah. So dia akan jadi flat macam tu. Right? Okay. Okay, again, the same thing, inductor current, inductor voltage, diode current, capacitor current, the same. Okay. But in practice, a finite capacitance will result in some fluctuation in output voltage or ripple. Again, there is no such thing as the absolute capacitance. Dia mesti ada ripple voltage ataupun ripple current. Satu lagi sebab another reason is we need that ripple current in order to determine what is the suitable capacitor that we're going to use for the system. Okay, the peak output ripple is calculated from the capacitor current waveform. The change in capacitor charge can be calculated as, so untuk capacitor ni, for the capacitor we see what is the change in charge, right? So from there we can see that delta VR over VR, which is this is the ripple voltage, is given by D over RC time the switching frequency, and therefore we can find what is the capacitor value by manipulating this equation. We got the C equal to D divided by R delta V0 over V0 times the switching frequency. Right. So this is how we calculate the value for the inductor and the capacitor. Okay. Do you have any question about the operation of the converter or something that you don't understand? or something that you want to ask me? Do you have any question? So far, boleh follow?
Boleh, sir.
Right. Alhamdulillah. Okay. Design a boost converter that delivers 80 volt from 4 ampere from 45 volt voltage source. The output voltage ripple should not exceed 1% of the switching frequency of 20 kHz. Designed for CCM. Right. Okay. First, we have to find always when you see a question, try to find out what parameters are being given. Okay, so the parameters given here is the output voltage 80 volt and output current equal to 4 amp, and the input voltage is 45 volt. The ripple is 1% and the switching frequency is 20 kilohertz, and it says that designed for CCM, continuous inductor current, or continuous conduction mode. First, we have to find what is the duty cycle. So in this case, duty cycle is given by V0 minus Bs over V0. So you have your duty cycle is 0.44. Then after that, you have to find what is the power. So you not have to find the power, but you have to find what is the load. So the load in this case is 80 volt divided by 4 amp equal to 20 ohm. So now you have the parameter which is enough for you to find what is the value for the capacitor and for the inductor. So for the inductor is given by RT over 2 divided by 1 minus duty cycle squared times duty cycle. So from there you can see what is the value for the inductor, which is 69 microhenry. And to ensure that your system is in CCM, so you increase 25%. 25%, then you get 86.24 microhenry. So from there, find what is the capacitor value. So the capacitor value, the requirement is to have 1% of voltage ripple. So delta V0 over V0 equal to 1%, which is 0.01. Therefore, put everything into the equation. You have your D, you have your R, the switching frequency is 20 kilohertz, then you have this one 0.01. So you will get 110 microfarad. Okay. So the average inductor current, min and max. What is the average inductor current for min and max? So what the average current is 7.175. That is the average current. And Imax equal to IL plus delta IL over 2. So put everything into the equation. You have your source voltage, you have your duty cycle, you have your frequency, which is 1 over, you have your time, which is 1 over frequency, and you have your inductance value. So from there you can find what is the IL max, which is 12.915 ampere, and IL min, IL minus delta IL over 2. And then you have 1.435. Okay? Right. So this is just the simulation. Okay, example number 2. The boost converter has an input of 5 volt. Jap. Untuk for the example just now, do you have any question? So far so good or blur? So, meninggal
No, sir.
Okay, aku dah meninggal masing-masing. Right. So, tengok example number 2. Example number 2. A boost converter has an input of 5 volt and output of 25 watt at 15 ohm. So, given that this is V in, this is V out, and this is V out. the minimum inductor current must be no less than 50% of the average inductor current. So it says that the ripple current must not less than 50% of the inductor current, and the output ripple is given by 1%. And it says that the switching frequency of 50 kHz specify the value of L and C. Okay. So daripada apa yang dia bagi kat sini, from what is given, we can find what is the value for the current. And actually it is not straightforward, but it is manageable. You already have the output power, you have the output voltage. From there you can find what is the output current. Then after that, from here you can find what is the minimum inductor current. Then times 2 you have the voltage ripple. Then you get your maximum inductor current. Then from the voltage ripple here, 1%, you already know you can find your inductor value, and you can find what is the resistance value from the power and the voltage. Then after that, just put everything into the equation, then you can solve the problem. Okay. Now, step number 1, find what is the resistance and what is the duty cycle. So we know that P equal to V squared over R. So R equal to V squared over P. 15 times 2 is 225. Divided by 25, then you get 9. So 9 ohm. So from there, we know that the transfer function or the equation of the Vs and Vout is given by Vout equal to 1 Vs over 1 minus D. Then from there, you can find what is the duty cycle, in which 0.67 in this case. Step number 2, find what is the average and minimum inductor current. So IL minimum, IL average is given by this equation. Then you get 511 amp. And then you will get your 50% of IL will be 2.25 IL min. Then after that, find the inductor. And from the inductor, got your inductor here, and you can find what is your capacitor value. In this case, 148.89 microfarad. Okay. This is what I mean by a theoretical calculation. You can see that, for example, your inductor is 13.13 microhenry and your capacitor 148.89 microfarad. So this is what your required for the converter. But good luck to find this value in any shop. They will not give you 13.13 microhenry and 148.89 microfarad. So you have to find what is closer to this value, which is 12 or 13 or 15 microhenry. And this one 150 micro or 200 micro, something like that. Then when you have this new value, you have to recalculate and find what is your new duty cycle and what is your new resistor or load resistor that you have to use for your converter. Okay. Okay. Next, we go into the discontinuous conduction mode, the DCM. And for the DCM, we have to make an assumption where the average inductor voltage is 0 and the average current in the diode is the same as the load current. Okay, so when the switch is on, when the switch is on, the voltage across inductor is Vs. Okay, fine. So you have your converter here. So you have your switcher, your diode there, and your load, and this is a boost converter. In case of you forgotten the circuit, so when the switch is on, the voltage across inductor is is ds. So complete loop here, and you have the voltage across the inductor is equal to your source voltage or input voltage. And when the switch is off, the inductor current is positive, the inductor voltage is Vs minus Vout. The inductor current decreases until it reaches zero and is prevented from going to negative by the diode. Okay, so maksud dia, bila dia dah habis, dia takkan boleh jadi negatif lah. But this diode will become reverse bias. Okay. When both switch are diode are off, the inductor current is zero. Okay. So this is the waveform of the DCM. You can see that this inductor will start charging here when the switch is on, and when the switch is off, you fall through the diode. Then after that, you will have a zero region here. So which means that the energy in the inductor is already all the energy is transferred up to the load. Okay. And for the voltage, we have a positive voltage and negative voltage and zero voltage. And for the diode, again, it's the same. This is the diode current. You have zero current during the first interval. Then you have a value here where the inductor is discharging. And then for the third period, it is zero. So this is what you mean by discontinuous, mean that it has a zero interval. So there is no current there, no voltage there in the inductor. So for the mathematical equation, now you have D, D1, and this is D2 or 0. So you have three interval, which is the first interval, the second interval, and the third interval. But we consider only for the first and the second one because there is no current, no voltage here, so everything is halt or everything is nothing happened there. So the condition is zero in current and voltage. So in this case, you have to consider the duty cycle for D1 and D2. It's given by the cross voltage. The voltage across the inductor is given by Vs times T plus T1 divided by D1. Average diode current will become half of inductor maximum inductor current times D1, and maximum current in DCM is given by Vs d times dt divided by L. So to find what is the value for D1, you substitute equation number 2 into equation number 1. Then you will find that D1 is V out over Vs times 2L over R dt. Right. So continue. When you substitute D1 into the following equation, what will happen is you will have the transfer function. So the transfer function is the with this term we call a transfer function for the boost converter. For the buck converter, it should be V out over Vs juga, tapi dia punya ni is D. But here for the DCM, the transfer function for the boost converter in DCM mode is given by this equation. Okay. The boost converter depends on a combination of circuit parameter RL, and frequency, including duty ratio in determining the mode of its operation. Yeah. Okay, we take a look at example number 3. The boost converter has the following parameter: Vs equal to 20 volt, T equal to 0.6, switching frequency 20 kHz. Now it is given the inductor value 100 microhenry and capacitor 100 microfarad, and R equal to 50 ohm. So from there we have to verify whether this converter is in DCM or CCM. Okay. So in order to verify that the inductor current is discontinuous, you have to know that IM min equal to 0. Right? Determine the new output voltage. So sekarang dia tak bagi, in this case it doesn't give the output voltage, so you have to find what is the output voltage. The output voltage is given by, so this is Vs sepatutnya, Vs over 2 times 1 plus square root 1 plus 2d squared RT divided by L, then you will get V out equal to 53.59 volt, and the maximum inductor current is V out dt over L is 6 ampere. So this is the waveform for the example. Okay, one thing that is not in the lectures note, but something that I want to share. Usually we try to avoid the DCM because of this current, because the inductor current. This inductor current will flow through the switch. So you will have a steep high current that will flow into the switch. So this high current is not good for the switch because the higher value of the current, the more heat is generated within the switch. So if we have this, we call it di dt. So this is di and this is dt. So if you have a high di dt, then mean that your switch will generate a lot of heat, but it will take time for the heat to be taken out. So if you have a very high switching frequency and high current, high DIDT, mean that sometimes, not sometimes, most of the time, the switch itself cannot handle the heat generated by the DIDT. So this is the main reason why most converter fail. You can see that converter keluar asap lah, apalah. So most of it is because of the DIDT, this rate of current. Furthermore, this is the we consider as the ideal condition. So if we have straight inductance, straight capacitance in the non-ideal condition punya converter, this one will become higher, and if it is higher, it's even worse for the converter. So that's why we try to avoid the DCM. But sometimes we need when we have to use the DCM mode. But most of the time we try to avoid. We're going for the CCM because it is more stable. Right. So as for conclusion, a boost converter is a converter that can step up the output voltage without the transformer. How we use the voltage? How is during the switch off? You can see that we have two voltage here. So that this voltage and this voltage is sum up and become equal to the output voltage. And the voltage of the inductor, although the voltage of the source is maintained, is fixed, but the voltage of the inductor depends on the value for duty cycle and the value of the inductance itself. So higher the value of the duty cycle, higher current or more energy stored in the inductor, and higher the voltage will be. So that is the fundamental of the boost converter. You have two component, two energy. One is the source and one is energy storage component, so that it can give you a higher voltage to the output. Right. So in term of component use, it is a high efficiency because of the single transistor or single MOSFET. Yes, it is, but it is not as good as you think. So the boost converter, you can say that if you have a duty cycle here, and you have a output voltage here. Or if you increase the duty cycle by logic, it become something like this. It goes high. So this is 1. Sorry, tak nampak sangat. So this is 1. So this is the relationship. Higher the duty cycle, higher the output voltage. But in reality, what will happen is it is not like that. What will happen? If we go there and drop down. So around the duty cycle 0.7, something like that. It is good up until 0.7 to 0.8. That is the maximum duty cycle that you can work with the boost converter. This is because the straight inductance and the straight capacitance will lead to the converter to fail. So it become something like that. Okay. So the input current is continuous, but at high peak current has to flow through the power transistor. This is something that I mentioned just now. The output voltage is very sensitive to change in duty cycle because you have a very steep here, and it might be difficult to stabilize the regulator. The average output current is less than average inductor current by factor of 1/D, and a much higher RMS current would flow through the filter capacitor, resulting in the use of larger filter capacitor and inductor than those of a buck converter. Right. So that is it. That is it for a boost converter. Next week we will take a look at example of boost converter calculation, design, how to design the boost converter, and soalan-soalan yang final year lah. Saya akan cari contoh-contoh soalan final year kalau ada berkenaan tentang boost converter ni. Kalau tak ada, saya akan cari lah sumber-sumber yang mana. Kita akan tengok macam mana kita nak design boost converter. So, any question guys?
No, sir.
No sir. Right.
Doctor,
Yes.
Doctor, how we know our design converter can be operate in boundary and then CCM and DCM mode?
Again, tak over clear. Play lagi?
How the converter that we design
Hmm.
is stable in boundary, DCM and DCM?
Ini soalan lab kan?
Yeah.
So, in reality, how you control a converter? You will have, okay, in reality there is a few factors. You will have a varying input voltage, and you will have a varying output voltage. It depends on point of load. Point of load ni maksud dia, it depend on the load connected to the converter. It can be that 2 or 3 load connected to the same converter. So, and that's 2, 3 load. Contohnya, you have load A, load B, and load C. It can be sometimes load A turn off, sometimes load B turn off, sometimes load C turn off, or it can be a combination. So when you have that combination, then your converter will either mean that when you have the combination of load change, mean that the current that being supplied by the converter also change, right? Because it depends on how much power that is going to be delivered. And because of that, the current will be different, and the average current will be different. And if you have a less current, then you will more likely to go into the DCM mode. So by varying the output resistor or output load, then you can observe the mode of operation of the converter. It can be sometimes it can be in DCM, it can be BCM, and it can be in DCM. How to design the converter? It takes saya tak boleh nak tulis kat sini. It takes whiteboard for me to explain it. But in simple words, you fix your range of the input voltage. Let's say from 10 to 50 volt, 10 to 20 volt, for example, and you design using your worst condition. The worst condition is to be your input voltage is low, the lowest, and your output voltage is the highest. That is the worst condition for the converter. Then after that, you set up your duty cycle for that condition, which is going to be the highest duty cycle for that condition. Then consider the highest the input voltage and the lowest output load, so that your converter work in the easiest mode. Then after that, you find what is your duty cycle. Then you will get your input voltage range, you will get your output voltage range, and you will get your duty cycle range. Then for that, you will have two value for the inductor, right? The first one is the worst condition. The second one is your the easiest condition. Then daripada situ you have to compromise your inductor value so that you can find what is the value for the CCM, for the DCM and the boundary condition. Okay, itu yang saya boleh cakap lah, yang boleh terang kat sini, right? Okay tak? Tak okay? Okay, buat dulu. Okay. Okay. Ada apa-apa lagi tak? So kalau tak ada apa-apa, the last slide is your attendance.
So, untuk test fokus buat converter.
Untuk test fokus kepada apa pun saya tak tahu lagi sebab saya tak buat lagi soalan. Tak ada idea lagi. Dia tengok kepada mood. Kalau mood saya kejam, saya bagi je komputer yang paling susah. Kalau mood saya baik, saya bagi je komputer paling senang. So kamu berdoa lah supaya mood saya baik, okay?
Okay.
Okay. Any other question? Fokus test sungguh kamu ni. Aduh, takut sungguh. So if you don't have any question, that's all for the class. Sorry, it's quite fast, and like I said, it's going to be fast because I don't have to explain the basics to you guys. And also, I hate doing online class. And for that, kalau tak ada apa-apa soalan lagi, so we stop here. Assalamualaikum warahmatullahi wabarakatuh. Selamat sejahtera. Have a good, pleasant, good evening. Right.
Thank you, Doctor.
Thank you, sir.
Thank you, sir.
Thank you,
Bye.
doctor.
Masih dah.
Thank you, sir.
Thank you, sir.
Thank you, doctor. Thank you.
Yang paling heran kan, dia paling heran adalah waktu kamu paling suka bercakap adalah waktu thank you sir. Waktu suruh tanya soalan, tak nak tanya soalan.
Betul, sir.
Betul. Alright, okay, see you guys in the lab session, okay?